Birkar from Cambridge. And Professor Birkar is a leading expert in birational geometry, especially in new model program. So, moreover, Professor Birkar was appointed as the NCTS Scholar starting from this year. So, which means that starting from this year, he will be visiting NCTS quite often. For the next 3 years, he will be here for at least 3 months or more. So this time he will be here for the whole September and going to give a lecture series on birational geometry in plastic characteristic. And so this is the first lecture, and next lecture will be on this Friday, and then also next week will be lecture 3 and lecture 4. And the week after Zhongqiujie, we will going to have lecture 5 and lecture 6. So they are going to have 6 lectures in this series. And I also prepared some handout. So this paper of Keel in annals, and also paper of Kashini Tanaka and Chunyang Xu, and also the paper of Heikan and Xu. So if you need this paper, then you are free to take one copy of this. Anyone else? Okay, so
okay, thank you. I would like to thank the institute, the department, and especially NCTS, and in particular Professor Birkar Chen, for making this whole thing possible. So I'm trying to give you some impression of what is birational geometry over positive characteristics, which can be quite different from birational geometry over complex numbers. So I try to remove technicalities as much as possible because I understand most of you about birational geometry. So there is no point in being very, very precise. So I just try to tell you some of the main ideas in this whole story. So let me start with pointing out this thing that, so the main truth of birational geometry is characteristic zero, which is essentially the same as over complex numbers as the following thing. So there are two very fundamental tools to do complex geometry, birational complex geometry. So the first one is resolution of singularities. So resolution of singularity essentially says in a not maybe most precise form, it says that if x, so let me all just fix one algebraically closed field throughout this lecture. So assume that now the characteristic of K is 0. So then the resolution of singularity says that if you take x to be as smooth as projective or even open, any variety. X is a variety over K. So variety usually means that it's irreducible. It has only one component and there is no non-reduced structure and so on. Just a classical variety. Over K, then there is a smooth projective variety y, which is birational to x. So this is the most rough, imprecise form of this statement. There are, of course, more precise statements how to resolve the singularities and whether you can leave the smooth points and so on. So I will not go into this detail. So the important thing is that if you start with any variety over this field, you can find another variety over the same field, which is birational to X. So hopefully you know what is birational. It just means that there are open sets which are isomorphic. So that's the meaning of birational. It means that you can ignore some part of your variety, and then what is left is exactly the same. They are isomorphic. So this is the theorem of Hironaka. And why this is very important? It's important because if you start from a random variety, you can replace it with something which is smooth. And especially because characteristic is 0, you could essentially assume that k is the complex number. Then it means that you start with any variety, you replace it with a manifold. And when you have a manifold, you have a lot of tools coming from differential geometry and topology and so on. So you can study your variety, maybe using analysis or differential geometry and so on. So that's why it's extremely important. That's one tool, and then the second tool is the so-called Kodara vanishing. Now again, the characteristic here is equal to 0. So this says that if x is smooth and projective, and if H is an ample line bundle, or I will just say divisor. So divisor and line bundle is here will be just the same thing. If you take H to be any ample, so ample, hopefully you know what is ample. It means that it has some positivity property. Then the statement is that the higher homology of minus, so maybe it's not a good notation, let me make it A. A then minus A is not going to be equal to 0 if I is less than the dimension of x. So this is the statement of the Kodara vanishing theorem. So in birational geometry, somehow this plays a really very central role. A lot of things that we prove go through these two fields. So let me give you some very maybe, again, not very precise, but very rough idea of how to use this kind of tool. Okay, so in birational geometry, for reasons maybe not very clear to you, is very often we like to prove the following thing. So we often have a line bundle, a divisor, let's say of the form L equal to some multiple of the canonical bundle plus some other divisor. So this is the kx is the canonical bundle. Here, let's say x is some variety. So the canonical bundle, hopefully you know that at least for smooth, x is just the top differential forms. And then this guy is also a divisor. Also in birational geometry, unlike the rest of algebraic geometry, we also allow rational coefficients. But you don't have to worry about that too much. And assume that this is some divisor which is effective. So in birational geometry, we very often come across this kind of divisors, and we like to show that this is base point free. so free here means that in a more general algebraic geometry language, it means that this bundle is generated by global sections. So if you don't know algebraic birational geometry, it may be very strange why we should look at these things. But if you work in birational geometry, you very, very quickly come across this kind of statements. You have a divisor of this form, and you like to show that this is base point free. And so, how you can do this? Well, the idea usually is to, the tree usually is the first thing you do is to make the singularities as simple as possible. So this is still characteristic. So the first step is this x and this divisor b may have very complicated singularities that is difficult to deal with them. The first step is to make them smooth or as simple as possible. And for that you can use this theorem of resolution of singularity. So we can make the singularities and can assume that xp is as simple as possible. So simple here is only in terms of singularity. And then the second step is try to apply this Kodara vanishing. And then we usually look for, or we try to write this L, which is m times P of the form numerically, or just let me just write the equivalent of the form kx plus some prime divisor plus something, which is m. So this S is just one smooth prime divisor. So it's just a codimension 1 variety with no singularity. Of course, if you pick a random setting, this is not going to be true. But we usually make the situation so that we can write it in this form. And then, so we have the exact sequence. So you have an exact sequence of this form. This is L minus S. You have L, and then you have a restriction to this sub-variety S. You have a natural exact sequence of sheaves of this form, and then you try to apply cohomology. And then what you get is something like this. You have some H0 of L, then it must be H0 L restricted to S, and then next step is H1 of L minus S, and so on. So from this short exact sequence, you will get a long exact sequence of cohomology. And then here the sections of L, the sections of L restricted to L, and then section of H1 of L minus S. But, so if you notice H1 of this, you can also write it as H1 of, just replace the L with this expression here, you remove the S and you get something kx plus some ample device. But then if you apply cell duality, then this is of dimension -1. And then you have to replace this. You remove the k, and what you get is just minus some ample device. So you have the dual of this space. But this is exactly the kind of thing which appears in the statement of the Kodaira vanishing. So you know that this is going to be equal to 0. So this space here is equal to 0, and this is just saying that every section of L restricted to S in fact comes from a section of L. So if L restricted to S is free, if it is generated by global sections, then L is free at least near S. So this is S, this is S, and then this whole thing will tell you that you can in fact understand your line boundary. You divide the L near in a maybe small neighborhood of this subrat. So if you really understand this trick, then you see that you understand half of birational geometry, because this appears so many times, it appears so frequently that that's why it's so fundamental. So these two tools, resolution of singularities and Kodaira vanishing, are really the basic blocks, the building blocks of birational geometry in characteristic 0. But let's see how about positive characteristics. Well, let's see how these tools work. Well, first of all, the resolution of singularities is known only up to dimension 3. So starting from dimension 4, you don't even know whether you take any variety if you can replace it by something which is smooth. So this is one of the biggest open questions in algebraic geometry. And if you want to get a field medal, then you can try to solve it. So this is not known, unfortunately, except for low dimension, and Kodaira vanishing. This just simply fails. So this one is even worse. It's not only conjecturally not known, it just fails. Even for dimension 2 it will fail. So it means that you simply cannot use these kind of tricks. And then of course then people started to think about other methods, maybe very different methods to replace at least the Kodaira vanishing. This one maybe you can just assume, hope that it's going to be true. Or up to dimension 3 you can just use it because it's already a theorem. But Kodaira vanishing doesn't work, and we have to replace it with something else. But unfortunately this is not the end of the story. There are even other bad things happening in characteristic P. So let me mention just a few of these problems. So we have generic smoothness. So there is a theorem in characteristic 0 which is extremely useful. This is just really not birational geometry. This is just very basic elementary algebraic geometry. So it says as follows that, so again here characteristic is equal to 0. Suppose that f from x to y is a morphism of variety, then x is smooth. So they don't have to be projectable or anything. Just x is smooth, y can have any singularity. The statement is that then there is some open subset of y is open such that the fiber over all the open in U are smooth. So this is the so-called generic smoothness. It means that generically, I mean, the general, most other fibers will be just smooth. They will not have any singularity. Maybe there will be finitely many, or more than finitely many fibers with singularities, but you can often ignore those and just concentrate on the typical. So the typical ones are smooth. I mean, this is like for human society, you say that maybe most people, a typical human is good, but there are also some bad ones. You can just ignore them. So the characteristic 0 is whole. But unfortunately, characteristic P, everyone can be bad. So I will just show you one example. So this fails in characteristic P. So I will give you as a very simple example. So the example is as follows. Let so now characteristic of A is positive, and the example is quite simple. So you just take x to be the variety defined by y squared plus x3 plus P plus T, and this is inside A3. So you have three coordinates, x, y, and t, and it will define for you something of dimension 2 inside A3. So this is the x, and I need to also say what is y, and then let y be just A1. So this will correspond to the coordinate. You don't know what it's spec and so on, you don't need to be scared. You just say that this is the axis essentially with coordinate t. Okay, and then F will be just projection. So it just means that if you have three coordinates, you ignore the first two and just leave the last one. Maybe I'm right. So A, B, and C just descend to C. And okay, so we can calculate the fibers of F. So the fiber of F over, let's say, let me say C in A1 is just, this is just the curve. In A2, which is given by the following equation, given by, you simply replace the T by C, y squared plus x3 plus C. So this is the equation of the fiber and the closed subset inside A2. So you see that A3 is just A2 times A1, and this is projection over A1. So the fibers here are just project a fine plane, and then the fibers of X will be curved inside A2. Anyway, so the fiber is defined by this equation, and then you can see that. So if I denote it by, let's say, phi, then you see the partial derivative and x is equal to 0, just because p, so you have p times x to the p minus 1. But p is a characteristic, so it will kill everything. And then you are left with y, and this is just 2 times y. So the first one is equal to 0, the second will be 0 if y is equal to 0. So in other words, you can always find a point on the fiber, which is simple. So all the fibers are singular. There is essentially no smooth fiber. So generic smoothness fails. So why this should be a big issue? The thing is that in birational geometry, or even more generally algebraic geometry, you often want to understand the variety using a fibration. So for example, if you look at the proof of the Weyl conjecture, it goes through some fibration. But there maybe it's not so important. But in birational geometry it's really important. You have often a fibration. You try to understand the fibers, the base, and then the total space. But if the fibers are not smooth, then that means that you cannot apply induction, or at least not very easily. So you really come across very bad situations. So not only you can have singularities on the fibers, but in fact the situation is even worse. You can have all non-reduced fibers. So this means that there are might have some singular points, but there is even extra non-reduced structures, non-classical structures that you have to take into account. So a typical example here is the following thing. So from now on, the characteristic will always be positive. So you just take x to be equal to y equal to n1. So let's say this is coordinate t, and then let f from x to y be given by, you just take a point A and send it to A to the p. So geometrically it's in this form, but algebraically, so this corresponds to the homomorphism of the ring which sends T to the P. So here the elements of the field, they are not touched. They will be sent to the same thing, but you change the T. From T equal to okay, now if you calculate the fibers of F, so assume that you take a point, let's say A, belonging to Y, and also assume that some number B to the P is equal to A. Then the fiber over this point A is given by the equation T minus B to the power P. So in other words, it has P multiplicity. At the point is just one point, but it has a non-reduced, non-trivial structure. But you can then also construct higher dimensional examples just by mimicking this situation. Okay. So you see that this can cause a lot of trouble, but characteristic P is not always such a terrible kind of territory. It also has advantages. So there are certain things in characteristic P that you can use which you don't have in characteristic 0. And it somehow all has to do with the following. True is the forbiddance. frobenius somehow is the cause and also somehow the solution of most problems in algebra. Birational geometry in characteristic P. So let me just define for you what is the frobenius. Suppose that X is a scheme, variety is any scheme over K. Then the frobenius is the following morphism. So usually denoted by F from X to itself. This is given by. So if you have two schemes and if you want to define a morphism, you need two things. You need one map just topologically on the topological spaces. You also need a map on the functions. You need to say where the functions should be sent. So this is defined by this. Topologically, it's just identity. So in other words, this map, it actually does not affect the topology at all. It's exactly the same. X will go to X, essentially. But on the functions, if you have F, you will send it to F on the P. So in other words, if you have a function F which is defined over X or some open subset, its pullback is defined to be F to the P. So this gives you a morphism. Locally, you can actually specify this easier. So for example, if X is a spec of some ring, then its frobenius just corresponds to the homomorphism of a ring from A to A, and here A, essentially these are just the functions. So F goes to the P. And in a way, this is really the whole. You can see the whole point here. So this map, which is defined in this form, this is the homomorphism of rings exactly because the characteristic is P. If you have characteristic 0, then this is not a morphism anymore because you see that F plus G goes to F plus G to the P, which is the same as F to the P plus G to the P. If characteristic is 0, this is not true anymore, so you cannot really define this sort of thing. So somehow this little point is really what gives this whole technique its power. So this is called, actually it has a little longer name, this is called the absolute frobenius. There is another kind of frobenius that I will tell you. This is defined essentially using the absolute frobenius, but it acts a little bit different. So by the way, if you have any questions, then you can just ask. Don't worry about it. Okay, let's see how is the geometric frobenius. So we have a diagram of this form. See that X is defined, this is a scheme of the variety defined over K. So this means that you have a structure map to a point, to the spec of K. And we define this absolute frobenius from X to itself. But for similar reasons, you also have a frobenius map on the point downstairs. So this is also a frobenius. This is just the map corresponding to the extension of K to K, which sends A to the P. So you have a natural diagram of this form. But, so you have two schemes defined over another scheme, then you can take the product. So here, it's not big enough. Let me make it a little bit. So you can take the product and then it will have to factorize in this form. You have stack of k. You have a new variety, a new scheme. We define it as stack of k times x over stack of k. This is just the product of these two over this guy. So you have a natural, by the universal property of product, you have this object is just the product, and you must have a morphism from x to this object, which makes the whole thing commutative. And the map here is called geometric property. So it's called geometric because it has a classical flavor. It can be also defined using just classical language. But the xp here is, in fact, the scheme is just the same as x. But we want to distinguish it from, especially from this x, because if you consider this xp as a scheme over the original field, its structure is very different from x over stack of k. So let me clarify this whole thing by one simple example. So suppose that here x is just a1 and this is stack of kt. Then we have this geometric diagram here. I can write the algebraic corresponding diagram, so corresponding the diagram that I just wrote, we have algebraically we have the following. So this morphism here is nothing but just the embedding on a field into kt. It's just a natural embedding. From this k to the second k, you just send every element a to the p. This is just a forbidden. And you have here one other kt, and this is again the natural embedding. You send here every f to the p. That's just the way I define the forbidden. But then we also have this blue thing in the middle. So if you write down the product, again this is just kt. So the first map here, what it does is it tells you that if you have a polynomial sigma, let's say ai t to the I, this goes to sigma ai to the p to the I. In other words, it just affects the coefficient, not the variable. But the second bit will just send t to the p. Here it will not affect the coefficient, but just changes the variable from t to the p. So I can also here write, so x to xt is really nothing but, so here you have just a1, you have just a1. In terms of coordinates, it just sends the point x. So with coordinate x, just send it to x to the p. So it just raises the coordinate to the p. And this corresponds to changing the variable from t to the p. So that's the story of the probability, but let me demonstrate why this probability is so important. So how do we use probability? So the probability can be used to deal with deepening of subscheme. So in what I will tell you, you will get the point what it's taking. If you have a subscheme of a closed subscheme of another scheme, you can make it thick. This doesn't make it in classical algebraic geometry, but using the language of schemes, this makes sense. But anyway, in what I tell you, it will be more clear. So as usual characteristic is positive. Suppose that this is a scheme over K, and suppose that D is an effective Cartesian divisor. So then here, because F is effective, you can also consider it as a closed subscheme of X. Now, if we apply the freeness to X, you can ask what happens to this device. So you have the pullback under the freeness of this divisor here is in fact nothing but P times D. So you see from X to X you have the freeness, you have a divisor T, you can pull it back and get another divisor. But in this case, what you get is the same divisor, except that now it has some multiplicity. It implies the divisor with P times. Let's say if you have one curve, or just one point, this has some scheme. The pullback that will give P times. So it has some non-reduced structure. In other words, this is a thickening of the original subscheme. So this guy is here, thick. And the reason for that is quite simple. So that's because Cartesian divisors are defined locally just by one equation. If it is locally defined by, let's say, some f, then the pullback is defined by f getting to the p. So the local equations just are raised to the power p, so that your Cartesian divisor will just multiply with the p. Okay, so that's when D is an effective divisor. But now suppose that we have another Cartesian divisor, maybe not effective. So the fact that the pullback is just multiplying by p, it has nothing to do with this effectiveness. It's true for any line bundle or any Cartesian divisor, because exactly for the same reason. So again, pullback of L is just p times L. Okay, now we have the following proof diagram. So I have here, I have X, to X is the freeness, I have D, so as I said, D can be considered as a closed subscheme. I have D is inverse image is just P times D, as a closed subscheme of X. The P times D is just a thickening of D, means that D itself is a closed subscheme of PD. And then from D to D you have MF, which is nothing but the freeness. So you have a diagram of this form. Now we also have the Cartesian divisor L here, and the pullback here is PF. So now I tell you why I consider this technicality. suppose that L is free. Well, L restricted to D. So as usual, free means generated by global sections. So when you have a line bundle, you restrict it to a subscheme, closed submajor subvariety. It's generated by global sections. Let's say it's very ample or something. But now, if I use this map here, let me call it pi, I can pull back my bundle here to PD. So now, the morphism pi will give you, so induces a map from the sections of L restricted to D to the sections of the pullbacks. In this case, the pullbacks are just PL restricted to PD. Now, if L restricted to D is generated by global sections, so all the sections are here. But these sections will go to sections of PL over PD. So in other words, if you have freeness here, you will get freeness there. So essentially for free. So this implies that PL on the closed subscheme PD is also free. So you notice that this doesn't claim that L is free, but you have to multiply by P. But still, for birational geometry, this is more than good enough. So in other words, the freeness gives you a way to say something about the thickening of a closed subscheme. In this case, just a Caucher Birkar. There is no such thing in birational geometry or algebraic geometry over characteristic zero. In fact, so many things fail just exactly because there is no such thing. So in other words, characteristic P also has these kind of really amazing advantages. So I will come back later, maybe in the third lecture, to this point. It forms one of the, you could say, the starting point of recent advances in birational geometry in characteristic P. So you could actually say, more generally, instead of a character divisor, if Y is or Z is Z is a closed subscheme. And if you take a thickening of this closed subscheme, so in other words, let's say Z and Z prime, we have two such that Z itself is a closed subscheme of Z prime, and they have the same reduced. So in other words, classically they are the same, but the non-reduced structures may be different. They might have different multiplicity. So for example, this could be any scheme, this could be some point, but this one could be maybe 3 times the point. Just has maybe more multiplicity. So this is what I mean by a thickening. You have a thicker closed subscheme. So you have a quite similar diagram. So to make it short, in fact, there is some E, some number E such that we have a factorization. Factorization of the Frobenius. You have Z to Z, this is a Frobenius, but maybe one Frobenius is not enough. Maybe you have to take one, another one, compose them together maybe E times, and then you have Z to Z prime, and then you have a morphism from Z prime to Z. In other words, somehow this thicker closed subscheme lives between Z and Z through this Frobenius morphism. So precisely for the same reason that I discussed, if you have Z global generation here, you can get it also on the prime. So if L restricted to Z is free, just because of this diagram, then you can say that PL, well, this P to the E, because you have E times freeness restricted to Z prime is also free. And the way that you construct this diagram is actually completely elementary. It's very simple. I will not do the details. Okay, let me go to another kind of go back to the bad stuff now. Leave this a good thing, and let's discuss another bad behavior characteristic P. So suppose now that X is, let's say, just a surface. Smooth projective variety over K. For the moment, assume that the characteristic of K is P. Then we have the following very important conjecture. So again, if you are thinking about field method, I think you better pay better attention. So this is one of the really fundamental open questions in birational geometry. It says that X is covered by rational curves. So rational curve is just essentially just P1, but a little bit maybe more complicated, just the image of the projective line. So X is covered by a rational curve if and only if, so I have to use here a little more advanced language, if and only if the quadratic dimension of X is none, so this is negative. But this itself, the meaning of this is that whatever number you take, and if you multiply the canonical bundle with this number, you don't have any sections. So in other words, there is no section even if you take very large multiples of the canonical bundle. So this is a statement about canonical bundles, and somehow this can be translated into a very different statement about rational curves. So this itself is known in dimension 3. But from dimension 4 and on, this is not known. But at least for surfaces and for threefold, we know that this is the case. However, the problem is that the characteristic P, even on surfaces, will fail. So this is not true. So I will just construct an example for you to see that this really fails. So again, the example will be very elementary, just to deal with some simple equations. Okay, the example, as I said, is quite elementary. You start with, so here I will concentrate on P equal to 3. This is a little bit simpler. So actually, so in the example, let's take just 3. Okay, you start with an elliptic curve inside the projective plane. So I can make it more explicit. So on the affine part, this is given by the following equation. Such that, so on the affine beta, if you ignore the infinity points, then on the affine part is given by this simple looking equation. So this is given by, just follow my notation, this is x squared minus 3q plus t equals to 0. So this is maybe the first example of an elliptic curve that you see in number theory or algebraic geometry. Okay, let's call this equation G, and then I will have more constructions. Then I take, now let y prime be defined by the following equation. We have y squared z plus x to the 3 plus t times z to the 3. Now this is inside P2 over C prime. So P2 product with C prime. So the t here comes from, this is a coordinate coming from below. It comes, it's a function of C prime. But I have these new coordinates, y, z, and x, and these other coordinates on P2. So I can define a closed subset inside P2 times C prime. So this is not really the example. We have to kind of modify things. Let me call this F. Now, the important thing about this y prime is the following thing, that there is some open subset C prime such that if you take a point, if y is y prime is mapped into this open subset, then y is so in other words, if you ignore just maybe a few points on C prime, then after you just have smooth points. So every point of y prime itself is a smooth variety. But also, and every fiber over points in U have at least one singular point. So maybe I will draw a picture. This statement could be a little bit confusing. So you have y prime itself, and this not a natural projection map onto C prime. So what I'm saying is that, let's take U here, just remove the C. And yeah, maybe y prime is a little bigger, you take the inverse image. So this is the inverse image of U. So what I'm saying is that the points of y prime themselves, they are smooth. But when you look at some fibers, actually every fiber, then the fibers might be of this form. Well, actually this is the correct thing, is this one. It has a cast singularity. But anyway, the point is that the fibers have singular points, but the total space itself does not have a singular point. It's smooth. It is really just very simple elementary stuff. So the fiber, over a point, let's say, and B inside U is just given by this equation. So you have y squared z plus x. The 3, you replace the t by just the second coordinate here. So you have a closed subset of P2 into the fiber over that point. And then you can see that here this guy has singular points. So for example, if z is equal to 1, In other words, if you ignore the points at the infinity, then so the equation will be y squared. You can just remove the set, then partial derivative with respect to x will just vanish, partial derivative with respect to y times y, and this is equal to 0. Y is equal to 0. So in other words, you can always find a singular point. And you can look at the other point. If x is not equal to 0, if x is 1, you have a singular curve. And to see that y prime is smooth, to see that the inverse image of u in y prime is smooth, so I will not do the calculation, but just use the fact that the y prime itself can be considered as a closed subset in P2 times A2. You replace the C prime by A2 because C prime itself is sitting inside A2. And this is just defined by, given by the two equations, f and g, and then to show that y prime is smooth, you just need to look at partial derivatives. So let's just do these calculations. Okay, so I have y prime, which is a surface. It's a variety of dimension 2, and it has this kind of curve. But this is still not the example I'm looking for. So next step is to take the closure that y inside P2 times C be the closure of y prime. So now this is a projective variety, the surface, projective surface, but it might have singular points. Now it could have a lot of singular points, it could also have non-normal things, but it really does not matter, you just take a resolution. So I take a resolution of singularities, then you could, for example, say that this should not modify the smooth point. So in other words, if a point is already smooth, you just leave it alone. You don't do anything with that. So in particular, this means that x to y is an isomorphism over the open set U. So now I look at the fibers of x over C. Finally, let phi from x to C be the projection, be the induced map. So the fibers of x over C, except finitely many of them, they are exactly the original fibers of y prime over U. So I already know. So by this fact here, it tells you that then, so the general fibers, actually all the fibers, for example, if you take a point in U, then the fiber over this point is singular. Actually, it's a singular rational. So look at the calculation that I did for the fiber. You see, just something defined by an equation of degree 3. So in particular, it means that the arithmetic genus is equal to 1. And then, because you already have some singular points, if you take the normalization, if you resolve the singularity, you just get a rational point. So it must be rational. so what I have at the end is a smooth projected surface over some curve, a smooth curve, but the fibers have singularities. So again, here is one example where the generic smoothness fails. But what is important about this example is the fact that, so if F, let's say G, if G is a general or it's just typical, or you could just take the generic fiber. Fiber of phi, then you can calculate by adjunction the canonical bundle with G. And this is just linearly trivial. And that's just because this fiber is defined by, so this is a curve inside P2 defined by an equation of degree 3. So this is defined as a sub of the curve inside P2 by equation of degree 3. And so you apply adjunction. So adjunction means that calculating essentially canonical bundle of some subrank. So why this is of any interest? Well, it's interesting because the G itself is rational. It's an image of a rational of P1. For P1, the canonical bundle is negative. But here canonical bundle is trivial, it's not negative. So this means that even though the G is rational, but it does not give you any negativity on X. It does not influence its negativity. So even though you have all these rational curves covering your surface, so you have all these rational, singular rational curves. So in particular, X is covered by all these rational curves, but X itself has no negative quadrilateral dimension. And one can show that quadrilateral dimension of X is non-negative. So again, I will remind you, this means that H0 of some multiple of K is not equal to 0. Yeah, you have this exactly thing. I mean, to see why you have this non-negativity is actually not really simple. So you could, here you could use either just classification, but it's not very interesting. Another more interesting thing is to use the eta. So eta relation says that the quadrilateral dimension of X is at least as much as quadrilateral dimension of the fiber, considered as a scheme, plus quadrilateral dimension of the base. But this is already non-negative. So there is a quite recent paper where this kind of statements are proved, and this is by Chen and Zhang. But there are so many Chen and Zhang that it may not uniquely identify this paper. So maybe I should write a little more precise detail. Chen. I'm not sure if there is more than one equation. I think you can find the paper. So this is again also interesting that you have this eta kind of problem that appear, and you have a surface covered by rational curves, but still it does not have negativity. It has, in fact, it behaves like the canonical bundle has sections, so you don't expect to have, for example, a negative curvature. But the curvature here will be still. The curvature will be more like. So So it's not exactly like varieties of general type, but it just doesn't behave like freeness. So P1 is a freeness, but it does not give you negativity on the variety itself. So again, this is something that happens only in characteristic P. If characteristic 0, you don't have this kind of strange behavior. So I have only a few minutes. I wanted also to discuss a counterexample to the Kodara vanishing, but these alone I think will take probably 1 hour, so I'd better stop here.
So, any questions?
Is there any possible replacement of rational curves to play the role in this conjecture?
You mean the Itaka or
No, the original the boundaries.
Yeah, I think the correct thing is that you it might be not so easy to formulate, but I mean here the example already shows. You have so if G is rational, some people will define its Kodara dimension to be negative because its normalization is a P1. But the correct thing is that it just somehow maybe forget about it, the fact that it's rational. Concentrate on the fact that its canonical boundary is already like positive and it's not negative. So you need maybe to replace that formulation by maybe looking at Kodara dimension of some varieties which are now negative, or in the statement it should be negative instead of just looking at what the normalization looks like. So I mean there is also, so right now, maybe later I will discuss the Itaka problem. So you also have a statement of this form. In classical algebra with birational geometry over complex numbers, this Kodara dimension, you go to a resolution and then you define Kodara dimension. But you can see obviously this really does not help, because here you will have minus infinity and then here you have 0, it doesn't tell you anything about x. So the correct thing is that to consider these scheme structures that appear on some variety, not to immediately go to the resolution. And you need to be careful when you go to the resolution. You need to also take into account the structures that come from the singularity. So in fact, even in characteristic 0, this already appears. So for example, if you look at just a curve of degree 3 which has this node of singularity. So this again is a rational thing, and if you go to the normalization, so you will have, instead of this point, you will have 2. So let's say this guy is equal to f, then again k of f is trivial. But to go on the normalization with the P1, you should not consider just k of P1. You also need to take into account these 2 points. So let's say P and Q, and then, so when you pull back K, you get KP1 plus P plus Q. In other words, you have to take into account this thing, you should not forget. And this is again trivial, which reflects this triviality more accurately.
Any other questions? So they can
So in the next lecture, I will try to tell you something about surface. This is again kind of classical, not very original. But I think it will still give you some ideas about the whole